Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is plugging with timers. Our objective is to employ a timer to briefly plug a motor in the opposite direction to rapidly decelerate it. This lecture operates under the assumption you've watched the plugging and timers lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. If you recall, plugging is the act of instantaneously reversing the direction of the rotating magnetic field produced by the stator. Plugging develops a counter torque and can be used to fully reverse a motor bypassing a stopped intermediary, or, if you time it just right, rapidly decelerate and stop the motor. In the plugging lecture, I introduced several circuits that have made use of rotational speed switches that did exactly that, only one of which is pictured here. For such applications, rotational speed switches are often called zero-speed switches. As the name implies, zero-speed switches are ordinarily activated into their opposite state at any speed above 0 RPM, although some may have adjustable speed settings. This particular circuit is intended to be unidirectional in nature, and that the applied phase sequence is L1, L2, L3 when the F contactor is closed. However, when a rotating rotor above 0 RPM in a particular direction is stopped, the activated rotational speed switch sees to it that the reversing plug-to-stop contactor applies phase sequence is L2, L1, L3 until the rotor reaches 0 RPM. The swapped phase sequence reverses direction of the rotating magnetic field produced by the stator and develops a counter torque to rapidly decelerate the moving motor. Once the rotor reaches 0 RPM, the rotational speed switch opens, returns the system to the de-energized start state. Note the electrical and mechanical interlocks prevent the simultaneous closure of the forward and reversing contactor. As serviceable as this circuit is, the fundamental weakness of this implementation is the rotational speed switch itself. Not only is the rotational speed switch a mechanical item composed of moving parts, it must be installed on a rotating shaft, which seriously complicates wiring and decreases longevity. Further complicating the finicky nature of a mechanical item is the dreadful possibility of the switch jamming in the closed position. If the rotational speed switch ever failed to open at 0 RPM, it would fail to de-energize the reversing plug-to-stop contactor coil. Upon rapidly decelerating, the plugging action would pass through the zero-speed state and continue to accelerate in the opposite direction. Not exactly the ideal result when your intention was to bring this motor to a rapid stop. For this reason, let's examine a couple different incantations of unidirectional plug-to-stop circuits making use of a solid-state timer to perform the exact same purpose. The timer, while not directly monitoring the real rotational speed of the motor, can be configured to briefly plug the motor in the opposite direction for the purposes of bringing it to a rapid stop. If this is a predictive, repetitive industrial process, the timer can be adjusted such that it stops plugging right when the rotor hits 0 RPM. The principal advantage of this circuit's making use of commonly available timers is that you don't need to rely on a rotational speed switch that has a very real possibility of mechanically failing. This being said, we're going to take the unusual step of examining a poorly designed unidirectional plug-to-stop circuit making use of a timer first. The reason I say it's poorly designed is because there's a flaw hidden deep within its design that I'm challenging you to root out. The motivated among you can also consider this as an opportunity to brainstorm alternative configurations. As I've stated previously, I am not asking you to design ladder logic diagrams, but rather interpret existing ones. Some of you, however, might be at the level of understanding where you can start suggesting changes to overcome some existing design flaw, or perhaps even design a system from scratch. The first system is making use of a timer relay in rung 4, executing the on-delay function. Let's say the timer is set to execute an on-delay of 2 seconds, which happens to be the exact time the motor needs to be plugged in the opposite direction to bring the motor to a rapid stop. The circuit makes of several operator inputs, notably a maintain contact E-stop, a momentary contact regular stop button, and a momentary contact mechanically interlock start and fast stop buttons. Before we begin an analysis of this system, it may be helpful to review the operation of an on-delay timer. Recall that a timing diagram of a timer executing the on-delay or delay on energized function would look like this. When the controlling input is energized, the associated contacts do not instantaneously switch to their opposite state. The normally closed time open contact remains closed, and the normally open time closed contact remains open. Only after the predetermined delay period has elapsed do the contacts change states. The normally closed time open contact opens, and the normally open time closed contact closes. When the controlling input is de-energized, the associated contacts quasi-instantaneously revert to their normal deactivated state. The normally closed time open contact recloses, and the normally open time closed contact reopens. With this background information in your pocket, I hereby issue this challenge. Pause the lecture and see if you can determine how this system works. And in doing so, see if you can identify a flaw with its behavior that may preclude this circuit from being used in an industrial environment. Since I'm feeling nice, I'll throw you a bone. First, the unidirectional plug-to-stop system making use of an on-delay timer does work, in that it will rapidly decelerate a moving rotor. However, it exhibits a peculiarity. If you want to discover this peculiarity, my recommendation is this. Think like an idiot and start randomly pressing buttons. Do not just sit there and wait for me to give you the answer. Pause the lecture and get to work. If you're tracking, you should have observed the following behavior. First, the intention of the operator interface buttons should be obvious. Start starts the motor in one direction. The e-stop and regular stop both serve to de-energize the motor, the difference being that the e-stop is maintained in nature and must be reset prior to returning the system to service. Fast stop, in contrast, rapidly plugs the motor in the opposite direction, bringing it to a rapid halt. Allow me to demonstrate this action. First, let me rid this diagram of the ugly dashed mechanical interlock between the two switches. You're just going to have to remember that fast stop and start are mechanically interlocked. An operator initiates this unidirectional system by pressing start. This energizes the F contactor coil, and the associated F contacts immediately change states. The F1 holding contact closes and allows an operator to release the start button. The F primary contacts close. The spring-applied electrically released brake is released, and the motor accelerates in one direction. If an operator wished to rapidly stop this motor, they would do so by pressing the fast stop button. The F contactor coil is de-energized, and its associated contacts immediately switch to their deactivated states. The F1 holding contact opens, as do the F primary contacts. Via the normally closed time open TR1A contact, the plug-to-stop reversing contactor coil is energized, as well as the controlling input of timer relay TR1. The contacts associated with plug-to-stop reversing contactor immediately change states. The R2 holding contact closes, allowing an operator to release the fast stop button. The R primary contacts close, immediately reversing applied phase sequence to the stator. The motor is plugged in the opposite direction. The normally closed time open contact TR1A, however, remains in the deactivated state while the timer executes the on-delay countdown of 1-2 seconds. After this on-delay period has elapsed, contact TR1A opens and de-energizes the plug-to-stop reversing contactor coil. Its associated contacts immediately change states. Contact R2 opens and removes the holding circuit. The primary R contacts open right when the decelerated rotor happens to reach 0 RPM. The spring-applied electrically released friction brakes lock the rotor in place. The controlling input of timer relay TR1 is de-energized, and the normally closed time open contact TR1A is reset back to its closed state. We've returned to the de-energized start state of this system. Thus far, everything seems to have worked as one would expect, and nothing out of the ordinary has been observed. This circuit, however, contains a flaw in that it is not foolproof. Those that discovered this flaw during my previously issued challenge will note that there is absolutely nothing preventing some fool from walking up to this system at rest and pressing fast stop. One might assume that fast stopping an already stopped motor wouldn't do anything, but for this particular circuit, that's far from the truth. The fool that presses fast stop in a motor at rest would be rewarded with a rather surprising result, in that this motor would start. Allow me to demonstrate. Given a system at rest, an operator presses the fast stop button. This would energize both the plug-to-stop reversing contactor coil and the controlling input of timer relay TR1. The contacts associated with the plug-to-stop reversing contactor coil would immediately change states. The R2 contact would close and establish a holding circuit. The R primary contacts would close, and the motor would accelerate in the opposite direction. After the on-delay period of 2 seconds has elapsed, the normally closed time-open contact TR1A opens and de-energizes the plug-to-stop reversing contactor coil. Its associated contacts would immediately return to their deactivated state. Contact R2 opens, removes the holding circuit, and the primary reversing contacts would open. The controlling input of timer relay TR1 would be de-energized, and the normally closed time-open contact TR1A would return to its deactivated closed state. In summary, this is not the safest system for an industrial environment, because an operator pressing fast stop would see a motor accelerate in the opposite direction for a brief 2-second period. This is to suggest that while functional when judiciously operated in a specific logical pattern, this system will not survive first contact with a fool. Given the population of fools you work with, it may be well worth the time and effort to consider an alternative configuration. Like I said previously, I am not asking you to design ladder logic diagrams, but rather interpret existing ones. This being said, you should be able to identify the source of the undesirable behavior for this particular system, and at least on a general level, suggest an alternative approach. By all means, pause the lecture and see if you can identify this problem, perhaps suggest an improvement. Keep in mind, there is no one right answer to this problem. My first inclination is to rethink how this timer is being used. Given a properly adjusted delay period, the timer does serve to decelerate and plug this motor to stop. However, the on-delay function seems to be rather indiscriminate in doing so. Perhaps a different general timer function can be chosen to better implement the system. Let's see if a negative edge-triggered one-shot and a slightly reconfigured circuit can do the job without any dangerous peculiarities. In this reconfigured circuit, I'm making use of a multifunction timer in rung 1, executing the negative edge-triggered one-shot. It may be helpful to review how a negative edge-triggered one-shot functions. The timing diagram for a negative edge-triggered one-shot appears here. This particular timer necessitates the internal circuitry be continuously powered up via the A1 to A2 coil connection and makes use of an additional auxiliary controlling input. The timer would execute the one-shot function only on the negative or falling edge of the auxiliary controlling input. If during an ongoing one-shot the coil is ever depowered, the one-shot would be cancelled and the associated contacts would return to their deactivated states. Rungs 2 and 3 contain the logic necessary for regular unidirectional operation. Finally, rung 4 contains the plug-to-stop reversing contactor coil that rapidly decelerates the motor. Note the mechanical interlock, the electrical interlocks provided by the R2 and F2 contacts, and contact TR1A associated with timer relay TR1 executing the negative edge-triggered one-shot function. Let's see if we can put this system to the test. Let's start by adjusting the timer to execute a 2-second one-shot, exactly the time necessary to rapidly decelerate this motor and bring it to a rapid halt. Note in the de-energized start state, the internal circuitry of timer relay TR1 is powered up. An operator initiates unidirectional operation by pressing start, and the F contactor coil is energized. The associated F contacts immediately change states. Contact F1 closes and establishes a holding circuit, allowing an operator to release the start button. The F2 electrical interlock opens. It prevents the plug-to-stop reversing contactor coil from being energized while in unidirectional operation. The F primary contacts close, and the spring-set electrically released brake is released, and the motor accelerates in the unidirectional direction. Additionally, note that timer relay TR1's controlling input is energized. However, this being a negative edge-triggered one-shot, it has not experienced a negative edge. If an operator wishes to rapidly decelerate this motor, they do so by pressing fast stop. This de-energizes the F contactor coil, and the controlling input of timer relay TR1 experiences a negative edge. The F1 contact opens and removes the holding circuit. The F2 electrical interlock closes, and the F primary contacts open. When the controlling input of timer relay TR1 is de-energized, it experiences a negative edge and executes the negative edge triggered one-shot function, and that contact TR1A closes for 2 seconds. This energizes the reversing contactor coil, and its associated contacts immediately change states. The R1 electrical interlock opens, preventing an operator from starting the motor while it is being plugged to stop. The plug to stop reversing primary contacts close, and the motor is decelerated in the opposite direction. Once the 2-second negative edge triggered one-shot function is elapsed, contact TR1A opens and de-energizes the reversing contactor coil. The R1 electrical interlock closes, and the R primary contacts open. The spring-applied electrically released brake is applied just as the decelerated motor reaches 0 RPM. As previously, the e-stop and regular stop would both serve to de-energize the motor and apply the friction brake. The difference being that the e-stop is maintained in nature and must be reset prior to returning the system to service. Opening either of these buttons would de-energize both contactor coils as well as completely depower the timer. Completely depowering the timer would cancel any ongoing negative edge triggered one-shot and reset it, bypassing the plug-to-stop deceleration period. In contrast to our previous implementation, note that this circuit does absolutely nothing when a full in full mode saunters along and presses fast stop when the system is at rest. Opening fast stop while at rest does not trigger the timer, since its already de-energized controlling input would not experience a negative or falling edge. This circuit, in my personal opinion, is a far safer implementation of a unidirectional motor that is rapidly decelerated via brief plugging action. The principal reason being that the timer executing the negative edge triggered one-shot is far more discriminatory in reacting to input than the on-delay function in our previous example. The larger moral of this story is that there exists a continuity of ladder logic quality from bad to good and covers all points in between, including circuits that work well as long as an operator judiciously follows a prescribed operation sequence and never once does something unexpected. The point is that well-designed systems should have a level of robustness that provides some resilience against the illogical dalliances of the fools that run them. By no means am I suggesting that this is the best ladder logic, nor is it the only way of implementing this function. However, it does at least serve to not unexpectedly energize a motor at rest when someone foolishly presses fast stop. Alternatively, this same circuit could make use of a timer relay executing the off delay function, also set for the same 2-second delay period, such that the rotor is decelerated to 0 RPM. The DC injection braking lecture, available at the Big Bad Tech channel, goes over a similar circuit, making use of an off delay timer. By all means, pause the lecture and see if you can walk yourself through this particular circuit to ensure it works as advertised. Really, the only difference between this implementation making use of an off delay and our original one making use of a negative edge triggered one-shot function is that normally open time open contact TR1A immediately closes while the motor is running and delays opening by 2 seconds. Regardless of the timer function employed, the electrical interlock provided by contact F2 in the activated open state while in unidirectional mode keeps the reversing contactor coil from being energized while in unidirectional run mode. A quick note on these timer functions. Note if the timer failed to plug the motor for a sufficient length of time to bring it to a standstill, the delay period can be adjusted. For example, the delay period can be increased to plug the motor longer, or decreased if the plugging action accelerates it in the opposite direction, passing through 0 RPM. Different loads would require different deceleration periods. Additionally, let me remind you that plugging a running motor in the opposite direction is electrically and physically demanding, and that contactors must be derated when used for this purpose. Frequently plugged motors would overload early due to the increased current draw of the plugging action. Additionally, plugging for this particular application is to be used to decelerate a moving motor only, not physically lock it in place. A mechanical device, like the spring-set electrically released friction brakes, are used for this purpose. In conclusion, this lecture took a brief look at different implementations of circuits that rapidly decelerate a unidirectional motor by briefly plugging it in the opposite direction. We discussed the limitations of mechanical rotational speed switches and examined several different timing functions: the on delay, the negative edge triggered one-shot, and the off-delay timer to yield the same result, albeit with different levels of robustness. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.